All right, ladies and gentlemen, welcome back to another round of AP Chemistry information. Today, we are going to be taking a look at the beer-lambert law and the experimental technique known as spectroscopy. Hopefully, you're ready to go here. I'm going to be saying a lot of stuff today that I am not going to write down. I hope you catch most of it. And if you don't understand it, get your questions written down. We'll take care of that in class. All right? Okay, so here we go, spectroscopy. Spectroscopy is essentially an experimental technique where we're going to measure how much of which wavelength of light is absorbed by a particular substance, all right? So we're going to measure how much of which particular wavelength of light is absorbed by a specific substance, all right? And so what we can do is if you really think about what we're doing, and this is not something that you are... right? If we've got a substance here that's got all these molecules in here, or a solution, if we take some light and we shine the light through here, the molecules actually are not going to let all of the light through. Some of them are going to absorb some of that light. So what we say is that if we take another solution, and now in this one we have way more of that particular substance, right? It's a higher concentration, and we still shine light through, in the second situation, we would expect less light to actually come out the other side, right? So less light would actually be transmitted in that particular case. And so what we do with spectroscopy is we rely on this phenomenon where the more of any particular substance is present, the more light is absorbed, i.e. the less light is actually transmitted through the particular solution. All right, and so I'll do this right now. I'm going to go ahead and pause the video, but I'm going to draw the internal structure of what a spectroscopy machine looks like. Okay, and so what I've got here is essentially the basic setup of a spectrophotometer. And so we've got a source of light. We're going to shine light into a sample. All right, the sample is going to absorb some of that light, and not all of it will be transmitted. So this term here, transmitted, that we're talking about, essentially is describing how much light actually makes it through the particular sample, because that's what we can measure. And then what we've got over here on the back end is a detector, and the detector, it gives us a percentage of how much light did we shine versus how much actually made it to the detector. So it'll give us this readout in a percentage, all right? And so a cool thing about this too is that we can actually use any part of the EM spectrum. And so if you think back to your pre-AP Chem days, the EM spectrum, these are our X-rays, our UV light, our infrared light, gamma rays, visible spectrum of light, radio waves. We've got all these different parts of the EM spectrum that we can actually use with spectrophotometry, all right? And so I'm going to go ahead and clear this out. We want to make sure that we understand the main ones that we can run across here is we've got UV, we've got visible, right? And then we've got X-ray spectroscopy. We also have infrared spectroscopy. And we want to understand that these two are based on, and actually these three are based on what we would call electronic motion. And what I mean by electronic motion is that there's enough energy in this part of the spectrum that we are actually going to be moving electrons. We're going to excite electrons, we're going to knock electrons off, and we're going to detect indirectly that particular electronic motion in some way or another. Infrared spectroscopy is a little bit different. Now, most of y'all have seen or heard of infrared spectroscopy because you've heard of like heat goggles, right? Like heat sensing, infrared technology, where if you take a look through the particular picture, it gives you a heat map of somebody's body. And what this is based on is molecular motion. Right? Because in the infrared spectrum, that part of the EM spectrum, there's not enough energy to actually get those electrons to excite. But what we can do is we can manipulate the rotational and the vibrational motion of the molecules and detect that motion. All right? And so I need you to understand the difference. UV, vis, and X-ray, we've got enough energy, we can knock some electrons around. For infrared, it's not as high energy, but it's still useful in a lot of different ways, but it's based on that rotational, vibrational, molecular motion. All right? Okay. What we are going to be focused on in this particular class is spectroscopy in the visible range, all right? And so we will look at that light, right, the Roy G. Biv that you remember, and we will be working with light in those particular wavelengths of light, okay? Now, the other thing that we need to understand, if we go back to the drawing that you've got right above this, our detectors, and I kind of said this, but I want to make sure that you understand it, detectors read transmittance, all right? They read transmittance. Now, a lot of these have computer programs that are part of the machine that actually will not spit out transmittance, but they will spit out an absorbance value. But I need you to understand the relationship here, all right? So even though it's reading transmittance, there is a relationship, a mathematical relationship, and absorbance is actually equal to the negative log of that percent transmittance, all right? So the negative log of transmittance, and what that does is that actually makes it a linear relationship, so it's directly proportional, and so we can just convert that transmittance directly into an absorbance value. I don't know if that'll come up at any point in time, but I need you to understand the spectrophotometer is reading transmittance, and it converts it to absorbance for us for a lot of times. But if you ever do run across a situation where you end up with getting transmittance data, it's pretty easy, just negative log of the transmittance, and actually give you your absorbance values that you can graph. Okay? All right. Now we're going to move on. We're going pretty fast here. Next thing we're going to do is we're going to take a look at something called lambda max. Now lambda, the symbol here is actually the abbreviation for wavelength. And so what we're doing here for lambda max is we are looking at the maximum absorbance for our molecule or our substance of interest. All right? And so what we'll get is we will have actually on the y-axis, we'll have absorbance. Over here, we'll have wavelengths, and we'll have anywhere from 500, 600, 700, and all the way up to about 900, especially if we're looking at the visible region. And what we'll do is with the machine, we will actually put a sample in there, and we will run it at every single wavelength. And it'll give us a readout that's very similar to this. And what you'll do is you'll see just a singular peak on it a lot of times, right? Sometimes you get more than one peak, but essentially what we're looking for is that maximum absorbance value, right? Where is our molecule the most efficient at absorbing light? Because what we can do is if we use that lambda max in our experiment, and that's the wavelength of light that we're shining into our sample, we can ensure with some confidence that the sample is absorbing the most light that it can actually absorb. All right, and so our lambda max, all you do to figure out what it is you'll get a readout like this, and you just read it over, and so this would be our absorbance value, and then down here, this would be our particular wavelength of light that we would want to use. All right, so make sure that you understand what lambda max is, and then the next thing that what we're going to do is, because we'll use that lambda max to test a sample of a stock solution. So for example, if we're interested in, say, copper, right, then we could actually put a solution and make a solution of varying concentrations, and I'm going to go ahead and clear this again. And what we want to do is we want to create a standard curve, and we did this in pre-AP, right, where we're going to graph absorbance versus concentration. We'll end up with a linear relationship in this y equals mx plus b format, right, where the y is our absorbance, the x is actually our concentration, and so we'll get this direct relationship between absorbance and concentration. And all we've done is we've got a set of samples that are diluted to different concentrations to give us this known linear relationship, all right? Now, I am going to go ahead and point out here, the slope here is something called the molar absorptivity, and then times actually path length. And what we'll do is we'll see, because we're going to relate this to the beer-lambert law, the equation that we've got. But understand that the slope is actually meaningful in this particular situation, just like it always is in our math anyway. So, all right, and so what we'll do now is we'll take a look at the beer-lambert law. All right, and the beer-lambert law is a really simple law. It's actually A equals A, B, C. All right, where the capital A is actually our absorbance, and you want to label because you'll need to know what these particular variables are. So A is our absorbance. The small a, this is our molar absorptivity. And so what we see is that with different solution backgrounds, with different wavelengths, we have this constant, I guess you could call it interference or this correction factor. And what molar absorptivity does is it allows us to actually correct for the solutions and the wavelengths that we are actually going to be taking a look at. The molar absorptivity is specific to any given wavelength. It's also specific to any given solution background that you've got. And so normally what we'll do is if we're going to be trying to test a particular sample, we'll figure out what the solution is made of, what the molecule is we are looking for. We'll figure out the lambda max, and then we can actually figure out when we graph, like when we came up here and we graphed this standard curve, and I guess I could label that. This would be our standard curve for our sample, right? Slash solution. This would be the name of that graph. And so we get that molar absorptivity value from there. The path length, which is B, is essentially how wide is our cuvette or our test tube that we're using to stick into the spectrophotometer. Generally speaking, this is always 1 centimeter. And so when you actually come up here to your standard curve, that's why sometimes we just ignore what that is and just say that our slope is our molar absorptivity, because a lot of the times our path length is just 1. And so it's not anything crazy, all right? And then for our C value here, this is what we're going to look at. This is our concentration. And so again, notice with this thing that absorbance and concentration are directly related, right? They're directly proportional. A high absorbance means I have a high concentration. A low absorbance means I have a low concentration, okay? And then one last thing before we leave you here is that our experimental results, there is a range of absorbance values that we want to try and stick between. For our range of absorbance values, we generally want it between 0.2 to 0.7. And so what we see is that anything below that or anything above that particular absorbance range is our light is either not scattered enough, right? And so we can't detect our concentration accurately, or if it's on the top end of that range and above 0.7 is we get too much scattering and it starts to actually interfere with the accuracy of our results. So if we end up with an absorbance outside of this particular range, what we can do is we can actually use the M1V1 equals M2V2 and just dilute out samples. Right? We can actually, especially if it's on the top end of the range, which is what normally occurs, if it's on the top end of the range, then all we do is we just dilute it out, and then it's still whatever absorbance we get from that dilution, we can determine the concentration of that solution in that particular compound that's in that solution. We know the concentration from that, and then we just have to do the M1V1 backwards. Right? And we have to back calculate back to what our original sample was going to be. I will show you some examples of that. I know that probably seems a little obscure hearing it in the lecture. We'll see some examples of that in class when we get there. Hopefully that's the end of this. And you got some questions written down. Hopefully, if you just wrote down what you saw on the screen, guys, this was a packed lecture with information. I said a lot of the things that you're going to need to know, and I did not write them down. So hopefully you got all that. If you didn't, please, for this one, I don't normally say this, but man, go back and watch this thing again because it's going to be kind of intense when you get into class. Make sure you got your questions down so we can get those answered and get those discussions started. And other than that, this is Mr. Doolin. I'm signing off. I will see you in class.